Thank you so much for the opportunity, and thank you for the very nice introduction to the journal. It's a brand new journal, and we're really excited to have people contributing to the content. So, in order to set the context for this first seminar, I want to give a brief introduction to what empathic computing is all about, and hopefully that way inspire some of you to submit to the journal or see whether or not your research aligns with the focus of the journal. So with empathic computing, the topic we're talking about is really about communication, and we all know how important communication is in our everyday lives. The Brazilian philosopher Paulo Freire says that only through communication can human life hold meaning. And because of that, over thousands of years, people have developed new ways to connect and communicate with each other. This is a small timeline showing uh, cave paintings 30,000 years ago through to carrier pigeons and radio and television to the multi-channel communication we have today. So when we look at the teleconferencing tools we have today, you see a wide variety of tools, Zoom like we're using here, mobile, teleconferencing suites, even telepresence robots like on the right. But with current technology, there's some limitations, and you can see first of all, there's a lack of spatial cues. So when you're talking to somebody on your phone, they blend with the background. The technology can support poor communication cues with limited support for gaze or gesture, and especially for awareness of the around surroundings of the person or environmental cues. And also, new technology introduces artificial seams between the physical and digital domains. So when I'm looking at my screen on my laptop, to collaborate with somebody, it's very difficult to keep the window of their face and focus while I'm still looking at the window showing the task space or what we're working on. So you have this separation between task and communication space. But there's new technology trends that can help overcome this. And some of the technology trends we're seeing now is improved content capture tools. So moving away from just sharing our faces to sharing our places. And you can see on the right, there's a picture of somebody wearing a camera on their head and then live streaming their view to a remote person. There's a lot more increased network bandwidth. So when I first started in computing 25 years ago, we had dial-up modems, and now we've got gigabit fiber connections, and so we can support very rich communication queues. And on the right, you can see an example of that used with augmented reality and being able to live stream an augmented reality virtual avatar of a remote person. And then also implicit understanding. So using AI and other technology to recognize our behavior and emotions from camera or audio feeds as well. So you can see there's three areas. One is very natural collaboration. The second is experience capture for capturing our surroundings. And the third is tools for implicit understanding and recognizing what people do. And so empathic computing is really the overlap of those three areas and looking at technologies that can explore this overlap space. And of course, most of us know or are familiar with what empathy is about. So Alfred Adler, the psychologist, said that empathy is seeing with the eyes of another, listening with the ears of another, and feeling with the heart of another. So the focus of empathic computing is really about can we build systems that allow us to share what we're seeing, hearing, and feeling with other people. And really, there's several aspects to that. So, first of all, systems that can understand your feelings and emotions. Secondly, systems that can help you better experience the world of other people. And thirdly, systems that help you better share the experience of other people as well. So, for the first, there's a wide range of sensing technology we can use to be able to capture people's physiological cues and feelings and map those to emotions. For the second, being able to better experience the world of others, then virtual reality is a really good technology for this. You can use virtual reality to go and visit locations you've never been before or to experience what somebody else is doing. And for sharing, so being able to share in real time what somebody else is doing, then augmented reality is a good technology for this. It allows you to overlay virtual information on the view of somebody while they're performing a task to help you better understand what they're doing. So I want to give you a couple of examples of those. But first of all, in terms of these three areas, there's been a lot of research being done in understanding people's emotions, and especially popularized by Ros Picard 20 years ago from the MIT Media Lab. And her and her research group and then others since then have developed a lot of systems that recognize emotions. A good example of that is Junreki Moto's work at the University of Tokyo or Sony CSL. And recently he did a project on combining smile detection with smart appliances. And I want to show you a small video of that. It's a little bit funny, but it gives you a nice example of how you can build systems that can recognize your emotions or your expressions and then respond to that. So I'm just going to fast forward a little bit. This is, here we go.
Smiling makes positive display
Yeah. Okay. So this is based on the idea from William James that
Physiology, William
we
James.
don't laugh because we're happy, but we're happy because we laugh. So if we can force people to smile, then that might make them feel happier. So he built a system for that. So I'll just mute the audio a little bit and play the video here.
Who was a psychologist and philosopher, said, "We don't laugh because we're happy. We're happy because we laugh."
So this is the system here. This is his happiness counter, and it's basically a Sony sub-shop camera inside a box. When you smile or you frown at the camera, it detects the expression and it will show it on those small LEDs. So you can see the lady here in front of the mirror, and when she smiles, the smile comes on in front of the mirror there. And so the way that works is it uses a Sony CyberShot camera, and the camera has some hardware in it to automatically detect smiling or frowning, and then it lights up a certain icon on the back of the screen. So putting a light sensor by that icon, you can then detect if the person's smiling or frowning. So you can see that working here. So it's a very simple way of building a system that will detect smiling or frowning. And then he used it in very interesting ways. So uh, in the first case, it's used to encourage people to smile. So here's the person brushing her hair. She's not smiling. So now it shows that she's frowning. So now it makes it smile on the mirror. But then in the second example, he looked at how you could use this to create a gateway to interacting with everyday objects. So here's a fridge. And the fridge has a magnetic lock on it. So you can open the door, but you have to pull very, very hard. But if you smile, then the lock's disabled. It's very easy to open the fridge. So now the person smiles at the fridge, and it's very, very easy to unlock the fridge. And so you can see it unlock there. So it's a very simple example of having a system that recognizes a very simple emotion. And because he's a computer scientist, he wanted to do a user study. So in a minute, you'll see a user study where he was able to use this with a man who perhaps wasn't smiling as much as he could have. And then you can check the people's response to that. So here's the field test. Here's the man they found. They found this kind of grumpy old man in Tokyo, and they put this into his fridge. And then every time he wanted to get food or open the fridge, he had to smile. And so here he is. This is the before picture. So actually not too grumpy. Looks kind of average looking there. And then he used the fridge for several weeks. And then you can see on the right hand side, this is what he looked like after using the fridge. Then this is 10 days after using the fridge. So, being forced to smile to eat made him look a little bit happier. So it's a little bit silly example, but of course you can many other examples of effective computing. The key thing though is with effective computer interfaces, most of them are single user systems. So basically measuring my emotions dealing with the system. So the second example, experiencing. So virtual reality is a really good technology to let people experience the world of others. Noni De Lupino, who's a famous journalist and VR documentarian, says that virtual reality offers a whole different medium to tell stories that really connect people and create an empathic connection. So one example of that is the Paint With Me project done a few years ago by Joy Jerry. And in this case, they recorded a stereo video of an artist painting on the left-hand side, and then the video is played back later on the right-hand side to a person in a VR headset with a set of paints as well. And so the person who was viewing the video really got to understand the feeling of the artist. So the artist would start painting and then describe what she's doing while she's painting and why she picked certain colors and what brush strokes she's making. And so for the person who was watching the video, it felt almost like they were inside the artist's body reproducing that. So those are two areas of using effective computing for emotion recognition, using virtual reality to help people experience the world of others. But in the experience case, in a many VR cases, this is all pre-recorded. In our work, we want to look at what we can do to allow people to share their hearing, so seeing what they're seeing, hearing, and feeling with others, but do that in a way that's live, not pre-recorded. So one example of that is this project by Andrea Valenti called Empathic Aura. And the goal of this project was to use augmented reality to show emotional state while you were talking face to face. So you can see a person here talking across the table with somebody else. The person on the right has a VR headset on with a pass-through video, and the person on the left is wearing an ECG, sorry, armband that measures her heart rate. And then we use augmented reality to show an emotional state around them. So I'll play the video here. So you can see here, you can talk with the person, and depending on their emotional state or stress level, there's this aura that appears around them. So how that works is we use an ECG sensor and a pre-trained neural network to map to arousal and valence, and then use that to show different colors around the person to give you some idea of how they're feeling. And then when Andrea did this, she ran a user study to see if people were better connected to the other person when they were using the system. So 16 or 12 users, 6 peers completed 3 tasks: watching film, completing a puzzle, and telling a story. And you compared to those people who felt that Aurea wasn't important. And what she found was there was a significant difference in task performance. You can see on the right or left-hand side here, the person using the AR system achieved a higher task performance in the Tangram block puzzle. But the person who was sharing the feelings felt somewhat more self-conscious and worried more about being self-conscious because the other person could see what they're feeling. And overall, though, the system created an increased personal connection for the people viewing the emotional content. So it felt some way of improving that connection between people. Our overall goal, though, is to enable people to share live remote experiences. So you can imagine, for example, sharing mountain biking down the side of a mountain or skiing down the side of a hill. And we want to try and mock this up. So one of the experiences we did about 6 or 7 years ago was to look at how we could share the first person view, but also share some emotional states. So we had the idea that people could be engaged in these tasks, and we could share their heart rate or other physiological cues to a remote person. And if they started feeling excited, then the person viewing those tasks should also feel excited. So we built a VR mock-up of that. So we built this VR system where you could be playing a game, and while you're playing the game, we would measure your heart rate using a special biometric glove, and we would stream that to somebody else who was the observer. And the observer was placed inside your virtual body, so they felt like they were in the same location as you, but they could hear and feel your heart rate. And so that the theory was that that would create an enhanced connection with the person who is streaming that view. And we built 2 different types of games: a butterfly world that's very calm, and a zombie world where you're in a dark room fighting zombies.
Effects of sharing physiological states of players in collaborative virtual reality gameplay. Our goal is to improve and enhance users' empathy among collaborators, especially in a remote setting using advanced computer interfaces. To support this study, we developed a collaborative VR framework which shares the player's position and heart rate to the observer in a virtual environment. The observers view the game from the player's position, but can rotate their head freely to look around. The player's heart rate is measured by a biometric glove. The measured heart rate is shared with the observer using both visual and audio cues. We developed 2 games based on this framework. The first game provides a calm and pleasing experience where the player catches butterflies while surrounded by nature. The second game presents a scary and stressful situation where the player tries to survive zombie attacks. We conducted a study to learn the effects of displaying the player's heart rate to the observer. From the insights gathered in this study, we present a set of guidelines for designing collaborative VR experiences.
So we presented that at in a journal paper about 6 or 7 years ago, and the key question was, what was the impact of sharing heart rate feedback with somebody else? And we measured the people's heart rate. We used the PANAS scale to measure emotion, and we also measured the sense of connection. And what we found was that those 2 environments created a significant difference in heart rate. The zombie environment was much scarier and created a higher heart rate. And sharing the heart rate significantly affected the positive effects, so made the people feel more connected with the other person and created this subjective connection between collaborators. So those are two examples of simple empathic experiences. One face-to-face, where you're able to see the emotions of somebody represented on them like a halo. The second one remote, where you've got a VR, people collaborating together. I wanted to show you several more examples, and then I'll talk about some research directions at the end. So an older project that kind of combines all these elements together is the Empathy Glasses project. In this project, we want to share the same communication cues that people have face to face but remotely. So when you're talking face to face, you can share face expression and eye gaze, but it's very difficult to share that when you're remote. And so we combine three technologies together: the an eye tracker, an AR display, and a special pair of glasses frames called effective wear glasses that could measure your face expression. And then we put that together in a system that allowed you to complete remote tasks. So here's a person wearing the system, and he live streams his camera view to a remote person. The remote person can then point on the camera view, and he will see their pointing appearing on uh, his view. But also, the remote person can also see their face expression and the eye gaze of the person doing the streaming. So you can see here on the bottom left, there's a face expression icon. And if you look very carefully in the picture on the right, you'll see a green dot. The green dot is the remote pointing cue given from the remote person. But right beside that is a red dot, and the red dot is the eye gaze of this person. So this is one of the first examples of a remote wearable system that allowed implicit non-verbal communication cues of eye gaze and pointing be shared. So here's a video of the system working. You can see the person wearing the technology there. In addition, he wore a heart rate sensor on his wrist, and then he's engaged in completing simple pictures out of blocks. And you can see here he's making the picture under the guidance of a remote person. So the remote person is now um, telling him which blocks to put. And then the remote person can tell him if he's paying attention or not because the red pointer will follow the green pointer. And that's really important because people always look at objects before they pick them up. So we have this implicit communication cue of whether or not the person's paying attention to his gaze or not. And then when he completed the blocks, he started smiling and the icon changed. So here's all the technology. The face expression sensor was done by using photosensors that can measure the distance between the skin and the glasses. So as you change face expression, we could measure that. And what we found in user studies was that by sharing these non-verbal communication cues, we about emotion and eye gaze and pointing, we created a stronger sense of connection between the people. But there's one problem with the system, and that it only shares the view of what the person's looking at. So in a follow-on system, we used 360 video sharing, and in this case, the person wears a 360-degree camera, live streams that to a remote person. The remote person can then can see what they're seeing and use hand gestures to communicate, and as well as voice, and then and that's streamed back to the person in the 360 camera view who's wearing AR glasses, so he can see this kind of ghost hands floating in front of him. And because we're showing a 360-degree video, the remote person can now use a VR headset to watch that. So here's a video of this working. In this case, we're looking at a fairly complicated power control panel. And there's the person wearing a HoloLens AR display with a 360 camera. We live streamed the camera view to a remote person, and then inside the AR display, he sees the remote person's hands appearing in his face, pointing at objects, and of course they can talk to each other as well. He's also seeing a green square. The green square shows where the remote person's looking because now they can look wherever they want. And so this is the remote person. And wherever they look, they're seeing 360 video from the person's viewpoint. So for him, it almost feels like he's standing inside the other person's body. And so it's a very powerful sense of telepresence, and they can communicate together very, very easily because he can point directly at the real world objects and highlight them using the AR cues. But you'll notice one significant problem with this is that the person who's remote is only seeing a 360-degree video from the real world, not a real 3D model, so they can't walk through the model and look at it from different angles. So in the most recent version of the software, we used a 3D live scene capture. So we have a cluster of depth sensors here, and we can take the point clouds from these depth sensors and fuse them together to create a live 3D a point cloud model. So you can see here, there's two parts. One is we've surrounded the real table with these 360 cameras. We can live stream that to a remote person in VR, and the remote person sees now a live virtual model of what's happening on the table. And then we can capture the person in VR's hand gestures and send them back to the person who's viewing the models in the real world with the augmented reality display so that they can now see augmented reality hand gestures from the remote person. So here's a video of that working. You can see the left-hand side is the AR view, the right-hand side is the person in VR. When they're gesturing to pick up the yellow object, the person picks up the yellow object, it disappears from the AR VR scene, and they're saying put it down the sand here, and they can now put the yellow object down and sees it appear again. And for the person in AR view, they see the remote user's hand gestures as a blue virtual hand icon. So it becomes a very, very natural way to collaborate together. And unlike the previous version, we have a 3D model of the environments the person can walk around. So you can see over time we've gone from just using 2D images to 360 and then to a full immersive 3D model, which means we've got increased immersion, better scene understanding, and better collaboration. So we're really moving towards that goal of being able to feel like you're standing in somebody else's body and seeing what they're seeing. One important thing though is that when you're collaborating between AR and VR and between the real world and remote experts is that you oftentimes use a virtual avatar to support remote communication. So you may not see my real body, but you may see a virtual representation of my real body. And what you can do is you can make some very interesting enhancements to that to improve the communication. So for example, in this case, we did a project of collaboration between somebody in AR and VR. And what we did, both people were represented as pink virtual avatars. You can see the pink heads there. But what we did is we added a virtual view frustrum there. So in the real world, when you talk to somebody, you can really only see what they're looking at when you can see their face. But in AR and VR, we can add this virtual pyramid that shows what they're looking at. So now we can see what they're looking at without seeing their face. So we thought that by sharing this view frustrum, we would, and sharing head pointing cues, we would significantly enhance the remote collaboration. So this is a video of that working. So on the left-hand side is the real space, the right-hand side is a virtual copy. And then in the AR view, you see this pink head in front of you, and those blue lines or pink lines coming out of the face shows the view frustrum. This is the VR view, so it's a virtual copy of the real world. And now I can see what the person's looking at, even if I can't see their face. So I can tell they're looking at that cube there. And then when they move closer, then I can see their face coming into view. So this provides a very powerful non-verbal communication cue. And we did a study to see what happened with and without using that mutual gaze. And what we found was that by using the mutual gaze, you see the head gaze on the right bar there, the blue lines, which is the amount of pointing people did, significantly decreased because we didn't need to use hand pointing anymore because we could tell the person was looking by using that virtual communication cue. So, so head gaze and eye gaze had a big impact on collaboration. You can also do other things as well, like for example, change people's body scale. So you can make people larger or smaller in VR when they're collaborating with each other. So here's an example of that. On the left-hand side, there's a person in VR, and on the right-hand side, there's a person in AR. And the person in VR is dropping cubes in the virtual environment, and while the person in AR looks at them. But now the person in VR has made themselves 4 times bigger. So now they appear like a giant, and in the AR view, if you can look up and see them looking down at you in the real world. And this might be very good for some sort of command and control applications where you want to monitor many people what they're doing. And so you can see lots of people at the same time working. And then we can also change our body scale to be much smaller as well. So in a second, you'll see the body scale shrinking in size. And now I can move into small parts of the virtual world copy of the real world. So now I'm 1/10 the size. And now for the person in the AR, they see me as a little virtual character in the real world. And the other important thing we thought about was that these communication cues don't necessarily have to be attached to the body. So you can see in this case here, we've got 2 people collaborating in VR, but on the right-hand side, you've got a person in VR who's behind their collaborator, and now they can't see what they're pointing at because the person's behind them. But what we can do is separate the communication cues from the virtual avatar. And so we built a system called Mini-Me. And the idea of Mini-Me was that when you couldn't see the person the life-size avatar of the person you're communicating with, you could create a miniature copy and put that in your view and always see that one. And that could use the same gaze and gesture cues to collaborate. And this is particularly important with things like AR head-mount displays, where the AR display may have a narrow field of view. And so because of that, you can't see the virtual person at the same time as the collaboration space. So this video shows that. Here's the problem here. Is that looking at the real table, you can see there's virtual overlays, but you can't see the virtual body of your collaborator at the same time as those overlays because your field of view is too small. So in this case, we create this little virtual avatar. You can see them coming into view there. And the avatar always appears where you can't see, when you can't see the life-size avatar. So now the avatar is pointing at this real block, and it's simulating what the case I just showed you before, where the person's behind you in the VR, pointing at this location. Now, even though I can't see the life-size avatar of my collaborator, I can see this little miniature copy, and it's pointing at the same location. So the mini-me appears whenever I can't see the life-size avatar. So now here's the life-size avatar, look away, and there's a little mini-me appearing, pointing at the same location. And we did some studies with that. What we found was that people performed faster when they had the mini-me appearing in their tasks. They felt more connected. So the person on the right saying, I felt like I was talking to my partner, even though I talked to this miniature copy. And there was a high sense of preference for the user case that had the mini-me condition. So the overall take-home message is that when you've got avatars representing remote people, you can start doing some interesting things with those avatars, like adding extra virtual cues, copying virtual scenes and placing them in the virtual scenes, using mini-me's and other things as well. So there's a lot of opportunity for research around how you can represent the avatars of the remote people you're communicating with, and how you can enhance those avatars to create that empathic connection. So the last thing I want to talk about was some research directions, and we've just scraped across a few examples of different projects, but there are many possible research directions. You can do research, for example, on sharing physiological cues, creating shared mixed reality experience, empathic shared mixed reality experiences, building empathic AI-driven agents, adding haptics and touch. There's also ethics and social considerations and many, many more examples. So I'll talk about a few of those, and then I'm sure many of you will think about your own examples that could apply in your own research. So first of all, sharing physiological cues. So the latest head-mount displays coming on the market are starting to integrate physiological sensors into the displays themselves. So the early research we did was very complicated because you had to wear an EEG cap and then a heart rate sensor and all these other sensors, and it was very difficult to collect all the data and synchronize it. But some new displays on the market, like the Galab from OpenBCI or the Cognition display, they integrate AR, VR displays with EEG and heart rate sensing and other things. And this then means we can capture and measure very important implicit communication cues like cognitive load or stress or emotion with many possible applications. So here's the glare display. And the key is that the glare and other displays, they have a faceplate that pushes against your face. And so because the faceplate is pushing against your face, you can put sensors in the faceplate to measure a wide range of things like the EMG sensors for measuring muscle movement, EOG sensors, or EDA and PPG sensors for heart rate. And the glare also has across the top of the head 8 EEG electrodes to measure brain activity as well. So all these things together means that we can measure a rich range of measurements that can be used to measure attention or facial expressions or arousal levels or cognitive load, and use that in very, very interesting ways. So, for example, in some more recent work, we did some work on measuring cognitive load in collaboration and training. So you can imagine a case where you're in VR with somebody else and you're supposed to train the person on a piece of equipment or a procedure. If you could measure their brain activity, you could measure how much they're understanding what you were training them. So we built a system that does that, that has avatars in VR, and then on top of the avatar, they have representation of your cognitive load and your attention level, and your heart rate. And so that you can see that on the bottom picture there, the little icons represent cognitive load. And here's a video of the system working. First of all, we had to measure people's default cognitive load, and we used an NBAC task. We had to remember numbers to remember their cognitive capacity. And then this is the virtual environment, and you can see the person's icon there. Then on top of their head, you can see this little brain appears that changes color depending on their cognitive load. So the brain right now, you'll see in a second, is red, and so that means it's a very high cognitive load. Now it's yellow, meaning normal cognitive load. And then there's also indicators of attention and heart rate as well. And what we found was that when we did this, that people had an overwhelming preference for being able to view cognitive load at the same time. Although people provided only a small amount of attention to the physiological cues because they were looking at what the person was doing as well. So there's lots of room for enhancement there. There's also an opportunity to create empathic shared mixed reality experiences where the VR or AR experiences change depending upon people's cognitive state. So we developed a system a few years ago that measured brain activity using EEG electrodes. And when two people engage in the same task, sometimes the electrical activity in the brain becomes synchronized. And you can use a technique called hyperscanning, which measures brain activity from both brains at the same time to detect the synchronization. So we built a mixed reality experience that changed depending upon the synchronization. So here's two people that are drumming together, and we had a system where you could drum with drumsticks in VR. You had three EEG electrodes, and then we had two people engaging in the drumming task at the same time, and that was then connected to a laptop that measured the PLV value, which is the phase value between the drum and the brain activity. So here's a video showing the system working. Let me just turn the volume up a little bit. And oops.
Neural Drum is a VR drumming experience that allows two players to drum together while their brain signals are simultaneously measured. At first you can set some daily objects on a table to use as drums. A player will use two drumming sticks to play the game. Both of the players will wear an EEG capturing hardware to get their brain signals measured from the frontal lobe. The data acquired will be streamed to the data processing system to enhance VR experience, depending on the player's collaborative performance. We designed a software to calculate the phase locking value, which is an index of neural synchronicity, for the FP1 and FP2 channels of the theta band from both the participants. When synchronization between two players is low, the camera will be more clear to do so, whereas when synchronization is high, the vision becomes more obscured with each point cloud eliciting higher particle effects. We logged and analyzed the user's brain signals, as well as had them answer a subjective questionnaire regarding their perception of synchronicity with their partner and the overall experience during a pilot study. We discussed design implications to further improve Neural Drum in our paper.
So we tried this out at the SIGGRAPH conference, and we looked at different people's performances. You can see on the left-hand side there's a player that's not very good, and so the green bars show when they're beating in time. And what happens is that the red line, which shows the trend, is quite wavy, so they're not very synchronized. On the right-hand side, there's a very good player where they're beating in time with the other person, and the red line is much smoother. And so we had good feedback from people saying they felt connected to the other person when they had that brain synchronization. So one person, for example, said, "It's quite interesting. I actually felt like my body was being exchanged with my partner." So as you saw in the video, when we had the synchronization, the view of the real world started to fade away, and it was replaced by a more VR experience with more special effects and visuals that immerse the player inside the VR experience, and the mixed reality part disappeared. So the next topic for research I want to talk about is intelligent virtual agents. And we've seen many examples of virtual agents evolving over time from the conversational agents that just appear in Siri or on your smart speaker to agents embedded in a screen, either in chat or in video. And then now we're starting to see agents embodied in 3D, so being able to experience mixed reality or virtual reality agents. So we've got this trend towards agents that have gone from voice menus to chatbots to photorealistic and digital humans. And the next trend really is towards empathic virtual agents. And so in this case, you combine three things here. One is empathic computing, AI-driven agents, and the third is mixed reality. And at the intersection of all these areas, you can see different interesting opportunities for research. So we can build empathic agents here. So these are agents that respond to your emotional state. We can build mixed reality agents here that are agents that exist in the real world. We can also build empathic MR experiences like the one I just showed you with the neural drum. And then at the intersection of all these three is the area of empathic mixed reality agents. So these are agents that exist in the real world but respond to your emotional state. And so if you're feeling stressed or overloaded when you're doing a task, the agent will change the feedback it gives to you. So one example of that, we built an empathic mixed reality agent that helped people perform a desert survival task. You can see the virtual character standing in the middle, and then it was supposed to help people pick objects that would be helpful for virtual sort of survival in the desert. And the person in this case wore an EEG cap, and the agent could measure the person's brain activity and then adjust its behavior depending on how the person was finding the task. So if the person was finding the task very hard, the agent would then provide more help. If the person was finding the task very easy, the agent provided less help. And then this led us to exploring remote touch. So Dasha Keltner, who's a psychologist, has said that touch is a fundamental language of human connection. But it turns out, even though touch is so important, there's very little research on remote touch, especially in AR and VR situations. So you can see the Scopus search here. I looked at haptic and touch in AR and VR, and it pulled up 12,500 papers. And then if you combine that with communication and collaboration, it drops down to about 1,500. And then if you combine it with collaboration and communication that's remote, it drops down to only 45 papers. So less than 1% of all the papers published on haptics and touch and VR and AR is around remote touch and remote haptics. So we've done some work in this space as well. And one in the previous example, I showed you the image of the person, the mixed reality agent helping with the survival problem. We made a version of that agent that exists in the real world, and then in this case, we let people feel touch on your forearm. So the agent would talk to you, and sometimes it would touch your arm, and you would feel the agent touching your arm. So to do that, we built the system on the left, this basically 10 vibrators that were connected to a control board that drove them all. And as the agent touched your arm, the vibrators would pulse, and you feel this kind of light touch or stroke on your arm. And then we did an experiment where the character provided recommendations, and sometimes it provided recommendations that were involved touch, and sometimes it didn't.
Hello there, I'm thrilled to embark on this desert survival game with you. We've got quite the adventure ahead, don't we? Among the items scattered on your left, let's start with securing the life-saving necessity that obviously stands out.
And so you can see the person start engaging with the agent, and they start arranging the items in order that I think are important, and then the agent will give you feedback. And we found we had three conditions. One condition where there was no agent, just giving haptic feedback. One condition where there was haptic feedback, and one condition there was an agent and haptic feedback together. And what we found, one condition was just a visual touch, so you could see the agent touching you, but you couldn't feel it. One condition where it was touched by itself with no agent, and one condition where the touch and the agent were to get felt at the same time. So we found that there was a significant difference in the realism when you could see the agent as well as feeling it touch compared to touching by itself. But the visual tactile touch condition where you combine all those three things together was by far the most preferred example. So people liked characters that could feel a sense of touch. But still very early days with the research, there's a lot more that can be done. So the last thing I want to mention that is all of this brings up huge ethical issues as well. So if we can detect people's emotions, you could imagine that over time we could also affect their emotions as well, and this could lead to behavior modification. If I'm wearing some sort of smart glasses all the time, all day, and then the system knows what makes me feel excited or sad, then it could trigger those feelings when it wants to. There's also obviously privacy concerns as well. So, if I can capture people's spaces and share them, then what's to stop me capturing your living room and sharing it with the people that might potentially want to rob you later and steal the brand new TV you've got, or doing face recognition and recording your physiological cues along with your face. And then there's some safety concerns. What's the long-term impact of having an AR VR display on your head, or having characters that try and distract you from the real world, or the long-term effects of using systems that modify or measure your emotions. So there's a very large amount of ethical and social relations work which needs to be done. So just to wrap up, we can see there's a lot of technology trends happening in this space. So at the top there, for example, there's an example of a Gaussian splat, and so we've got technology now that can create almost photorealistic 3D spaces from camera views. We've got very advanced displays. You can see there the Meta Orion display that will come to market in a couple of years' time. So it looks like real glasses, but can provide an AR VR experience. We've got natural gesture interaction, eye tracking, and then also emotion sharing. as well. And we've got these devices like I showed you before with sensors and the physiological sensors on the headset. So we talked already about these three areas, but then around all of this is this cloud of AI. And so, of course, AI has a big impact on all these spaces as well. And combining these technology trends together with AI might lead you towards what you could call empathic teleexistence. And so the idea of empathic teleexistence is that you can move people from being an observer to remote experiences to being a participant. And you can start exchanging more implicit communication cues like face expression or gaze or heart rate. And by doing that, you can create this really experiential collaboration. So you can feel like you're really doing things together. This is a screenshot from a Black Mirror episode where they imagine technologies that will allow you to really experience what somebody's feeling and feel like you're inside somebody's brain. So we might have a trend towards that area as well. So it could dramatically change how people collaborate and communicate together. So just to wrap up, I've talked a little bit about what empathic computing is. So it's really about creating systems that increase understanding. The key aspects of empathic computing is being able to capture and share your experiences, your scenes you're in, your surroundings, perform emotion recognition and sharing, and then also use communication cues and using new technology to share communication cues like gaze and gesture in new ways. And there are many opportunities for research, and I've talked a little bit about empathic MR agents adding touch and ethics and societal concerns, etc. So just to bring it back to the journal again, as John mentioned at the beginning, we're looking for submissions, any topic relevant to empathic computing as I've described it. It's open access and free to publish. And if you scan that QR code, that'll take you to a form where you can put in your interest level in terms of putting together a special issue or what papers you might have to be able to present. So the last thing and probably the most important thing is that the research I showed, some of it wasn't from my lab, some was from my lab, and the research from my lab wasn't my own work, it was the work of all these people here. So I have a lab in two places with about 40 people doing a lot of very interesting research and projects. And so if this is interesting for you, please visit our lab website, or you can email me, or you can follow me on Twitter. So thank you very much for your time, and I think we have a little bit of time now for questions.
All right, exactly. Thank you very, very much, Mark, for this talk. I saw that already some questions were popping in. I will just share to the discussion slide. Here we go. All right. And yeah, as indicated here, and I also wrote it in the chat, which I will have to activate. I kind of lost the chat. So you can drop messages in the chat or raise your hands so that you are being switched to unmuted, and then you can also ask questions there. So Mark is posting the links in the chat, I see. And I'm scrolling up now. Lutfi Arif had a question early on. I believe it's regarding one of the studies you presented, Mark. And the question is whether the cognitive load was also affected by the VR experience itself, especially for people using VR for the first time, and if in the study you differentiated this from the cognitive load caused by the VR content, such as learning material. Maybe, Lutfi, you could precise. I believe this is the study with the cognitive load indicator, but if it's not, please drop a line in the chat. Mark, do you see the question?
Yes, yes. So in that experiment, the people that did the experiment were all experienced VR users, and so we didn't think there was be much cognitive load increase by being in VR. But the task they were doing was learning how to disassemble a motorbike engine, and none of them had experience with motorbike engines, and so that dramatically increased their cognitive load. So yeah, so these were all it was a pilot study done with people from my lab, so they were all people that were very experienced VR users, so that we didn't anticipate there will be any additional cognitive load by doing that. But that's a very good question because, of course, people that are novice, they will definitely have some cognitive load effects there.
Yeah, indeed. I mean, usually, um, If you experience it for the first time, that creates additional signals, but there's learning effects. I think there's another question of Benjamin Chibik. Many empathic computing prototypes center on strengthening human-human connection. Do you also see room for empathic systems that mediate relationships between people and AI companions, say in games or workplace tools, and how those agents affect long-term well-being slash mental health? For example, AI companions like Replica, XAI Amy, or in-world AI NPCs.
Yes, so it probably wasn't very clear, but the last video I showed with the game with the empathic mixed reality character, that wasn't between real people, that was between a person playing the game, the desert survival game, and the mixed reality character. So in that case, the character was changing its behavior depending upon your cognitive load. And I didn't include this, but we've also done other experiences which are more game-like. So we did another game where you were playing in mixed reality and you would see spaceships coming through the roof of the real building, and you had to shoot the spaceships before they shot you. And then we had an AI agent that was trying to help you play the game better. So the AI agent was providing in words of encouragement and also telling you where the spaceships were going to be coming from. And the agent's behavior changed depending upon your stress level. So that's also an example of using um, empathic computing to enhance your engagement with an AI character or virtual character. And what we found in this case is that because people could, because the agent customized its behavior depending upon your emotional state, people felt the agent was a lot more helpful and felt the advice given was more personalized and better for them than just generic advice. We haven't done any research in robotics yet because the cost and time of working with real robots, but certainly the same thing would happen with robots as well. You could easily imagine robots that would recognize your emotional state and adjust their behavior depending upon that.
Okay. Thank you very much. I don't see further questions in
Uh,
the chat,
there's a
but please
commenter
drop
from
them.
Andrea that's talking about audio augmented reality. So she cited one of my earlier
Okay.
papers and they're interested in participating in collaboration on audio augmented reality. And I think this is very important. We, especially in the context of multi-party communication. So the paper she's referring to is a work we did where we had one person in in VR that was being guided, but that was guiding somebody in the real world to find locations. And so in this case, we had a virtual copy of a very large space, and the person in VR, as they move through, the person in the real world would hear their voice coming from the location at different parts. So the spatial audio provided a very important cue to guide them in that location. But the key thing was that it provided a very high realism cue. And we've done some other studies that look at when you have two or three or four or five more people all talking to you, when you use spatial augmented reality, you can distinguish between those speakers. So there's a big opportunity for using audio augmented reality to create more understandable empathic spaces. In fact, even with Zoom, and I'm surprised Zoom hasn't done this yet, but if you're on a Zoom call with 5 or 10 people, if they all start speaking at the same time, it's very hard to understand them. But even if we're on a Zoom call on laptops, we could spatialize the audio and create the impression that we've got people surrounding us in space. And then those people could speak to you at the same time, just like they do at a cocktail party or some event. And you could quite easily distinguish between the different speakers that you're different speakers that are listening or speaking. So there's a big opportunity in the audio space as well. And you've seen that also with the Meta Ray-Ban glasses and other AI smart glasses that don't have physical displays but use audio very effectively as well. So certainly I'd love to collaborate with some people on that. And then Shabazz asks questions if a journal exclusively considers manuscripts related to empathic computing audio except submission of other topics. It's so we just certainly don't have to have empathic computing in the title of the articles, but they should relate somewhat to collaboration or emotion understanding or empathy in some way or other. But it's still quite broad. So you'll notice from some of the articles that have been published, they only touch on that in a peripheral way, but whereas some are directly on that put that as your main topic. So if your article includes some aspect of collaboration, then certainly it'll be fitting well. Or if it includes some aspects of scene understanding or emotion understanding, and that also would work very well as well. But my advice probably would be to look at the articles we've already published and see if your article is similar to that. And then regardless, submit anyway, and we'll have a very quick turnaround time in terms of whether or not we'll consider it for review or not. And so you won't be waiting for months to discover whether or not it's appropriate. We'll get back to you very, very quickly. And if it's not appropriate, we'll suggest other journals that might be more appropriate for.
In general, also to chime in here, if you're working on something that can be considered an enabling technology, that is an aspect of empathic computing, for instance, affective computing, that's a puzzle piece, if you like. That's obviously not empathic computing per se, but it's definitely part of this. So please feel free, as Mark said, to submit.
Yes, definitely. We'll definitely accept those.
Okay, so good. I mean, we
The other
have
thing I should also mention with the journal is that we're still looking for special topics. So you may have a topic which is adjacent to empathic computing, and if you think you can get some other people to submit papers on that topic, then by all means propose that. So, for example, you might decide, well, I really want to propose a topic around human-robot collaboration, and and if you include some aspect of, emotion recognition when you're interacting with robots, then we could have a whole special issue on human-robot collaboration, which is a little bit outside the main focus of empathic computing, but certainly would be happy to host special topics or special issues.
Mhm.
And if you do have something in mind, please just fill in the form link I sent you with, and you can list there what you're thinking about, and we'll give you some feedback based on that.
Okay, so I think there's a follow-up question that is more related to a master thesis and the topic. So I guess we can skip that in the discussion, but we'll get
Yeah,
back to
just email
Benjamin.
me. Yeah, email me, Benjamin. That's great. Just email
Yeah,
me, and I'll be happy to give you feedback.
yeah. Um, Perfect. So I cannot see if somebody has their hands raised. So if I may ask one question myself, maybe. Um,
Sure.
Mark, have you looked into how also cultural differences play a role in designing empathic systems? Because obviously we have biosensing, we have all these technologies that we look into. Um, but again, we usually find that, for instance, in intelligent virtual agents, there's also cultural differences in terms of how the responses should be communicated and how collaboration works best. So is that also a
That's
topic of
that,
interest?
definitely that's a very good question. We've done a little bit of work on that, but not so much. And it's work we need to do a lot more. And so, for example, in some cultures, gestures are used very differently. If you are in Korea or in China, when you want somebody to come towards you, you move your hand down like this. But in the West, it's more like moving a motion like this. So it's the same intent, but a very different gesture. So if you're building, for example, gesture or recognition systems that associate emotions or and intent with the gestures, then it's very important for you to know the cultural background of the people using the system. And similarly, there's a lot of unexplored research, I think, in mapping physiological cues and face expressions to different emotional states. So we've done a little bit of work on that, but very, very little, and I think it's a huge area of opportunity as well. So, and certainly if we're going to build AI-driven agents that are supposed to interact with people, then we better make sure the agents know the cultural background and adapt their behaviors to the people they're interacting with. Otherwise, it'll feel very strange for those people.
Hmm.
So that's a great topic.
Um,
So Fisher asked if the presentation will be included. Actually, I don't think we recorded the presentation, which is an oversight on our half. I'm not sure, Jen, if you know if that happened.
I do think it's recorded.
Oh, great,
So
perfect,
I
great.
do think we will also share the Q&A session. So Phil, it's a good news
Lovely.
for you.